Let us resume our discussion in section 2. Previously, we went through orbits. Now the next topic is cycle. Let's begin. A permutation sigma is called a cycle if it has no more than one orbit with more than one element. And the length of the longest orbit is called the length of a cycle. Do you understand the definition? In case you don't, let's work out some examples. Here's an example of a cycle. We have an orbit 1 stays at 1, which has length 1. 5 stays at 5, which has length 1. 6 stays at 6, that too has length 1. But then again, look at this blue part. 2 goes to 3, and 3 goes to 4, and then 4 goes to 2, and 2 comes back to 3. We have an orbit of length 3 there. And this thing is called a cycle. It's called a 3 cycle because the length of this longest orbit is 3. And here's an example that is not a cycle. 1 stays at 1, that has orbit length of 1, good. And then we have blue, 2, 3, 4, okay, we have an orbit of length 3. And then look at this red part. 5 goes to 6, and 6 come back to 5. So we have an orbit of length 2. So we have 2 orbits of lengths greater than 1, a 3 orbit and 2 orbits, so this is not a cycle. This one is because we have blue, which is a 3 cycle, orbit of 3, yeah, and then otherwise just trivial orbits, just staying at the same place, just length of 1. So cycle, yes. This one is not. We often express a cycle with non-trivial parts only. So here, just throw away 5, 6, and 1, and just write 2, 3, 4 like this. So the blue part only. 2, 3, 4. So 2 goes to 3, 3 goes to 4, and then 4 comes back to 2, and then go back again. Same thing repeats. And then it's a little bit difficult to typeset for me, but you can do something like this as well. So 2, something's not right. Okay, so 2, 3, 4. So you can see this kind of relation. So it looks really like a cycle, right? Here's another example. And 1 stays at 1, 4 stays at 1, but 2 goes to 3, 3 goes to 6, 6 goes to 5, and 5 goes to 2. So we have this cycle of 4. 2, 3, 6, 5. So 2 goes to 3, 3 goes to 6, 6 goes to 5, 5 goes to 2, back to 2, and then continues over. And of course, you can write like this as well. So 2, 3, 6, 5, and then 2 goes to 3, 3 goes to 6, 6 goes to 5, 5 goes to 2 back again, and then repeat. Yeah, this one really looks like a cycle. But of course, those are difficult to typeset. So I'll use these notation, 2, 3, 4, 2, 3, 6, 5, those kind of things. And you can imagine the cycle structure. Finally, 2 or more cycles are called disjoint if all their non-trivial orbits are disjoint. And here's an example. we have a permutation sigma, and 1 goes to 3, 3 goes to 6, 6 comes back to 1, and that's blue, and 2 goes to 8, 8 goes to 2, and then we have 2 cycle, and then brown part, 4 goes to 7, 7 goes to 5, 5 goes to 4, cycle repeat, brown, and then a trivial orbit, 9 stays 9, and then we get 1, 3, 6, there's a cycle, 2, 8, another cycle green, and then 4, 7, 5, another cycle brown, and it turns out that the sigma is a multiplication of those. But then again, it turns out disjoint cycles commute. So even if we change the order, doesn't matter, because you see, permutations in general are not commutative. You're using composite functions, and composite functions in general are not commutative. But in case those cycles are disjoint, yes, they are commutative. And then in this particular case, there are 6 different orders because we are talking about 3 different circles, blue, green, and brown. So 3 factorial is 6, so there are 6 different orders. They're all the same. As a matter of fact, what we are going to do next is every permutation can be decomposed by disjoint cycles like this. And, oh, excuse me, here there should not be comma there. All right, sorry about that. So that should be multiplication. So I'll change this, I'll correct this typo. Oh, this typo left me off track. Where was I? We have disjoint cycles, okay, all right. And then disjoint cycles commute, so order doesn't matter. Yeah, we discussed those. Now what we are going to do next is every permutation can be decomposed by a product of disjoint cycles. And not only that, that decomposition is unique. Of course, order doesn't matter because disjoint cycles are commutative. So just selection. Here, blue, green times brown, and no particular order because they're all commutative, but there is no other way to decompose it. Some people call it cyclic decomposition theorem, a bit too formidable. So I'll simply say decomposition by cycles, just like I used previous term, decomposition by orbits. So every permutation of a finite set is a product of disjoint cycles. How do you prove that? Well, begin with that permutation, whatever permutation, let's say sigma, and that sigma will have disjoint orbit. And the starting set capital A will be decomposed by those orbits, say B1, B2, B3, all the way over to BR. Remember that? The reason is because being in the same orbit is actually an equivalence relation. So being equivalent classes, the orbits are either disjoint or identical, and if you union them all, you're going to get a decomposition. So that's what we can do, and let's suppose that we decomposed to B1, B2, B3 all the way over to BR. And that's given by sigma. Okay? Every permutation, so given any permutation sigma. And then let's define cycles sigma I like this. In each orbit, we do sigma x. So from x, we do sigma x and sigma square x, sigma to the cube x, until we come back. And the length of that cycle is, say, Li, then it'll go Li. Otherwise, stay the same. And then we'll have this multiplication. And then sigma 1 will just shuffle around B1, and B2 to BR will not be affected. And then sigma 2 will be just shuffle around B2, and so on and so forth. And then the uniqueness follows from the equivalence relation. That's it. Every permutation is a finite set. Every permutation of a finite set is a product of disjoint cycles. We proved it. And then we'll have some computation problems, but that's left as homework. And that completes section 2 of this notebook. We're going to meet again in section 3.